All right, I'm going to jump around a little bit in these Skill 7 Part 2 notes. And I'm going to start with E and then go to D and then go back to C because I feel like this is pretty much where we left off in class. Now, remember, we must always factor if possible to see if there are terms that cancel out. So for example, E in the denominator, we can factor that quadratic to be x minus 5 times x plus 3. And in the numerator, we have x minus 5. Now, this is super important for us to be able to see so that we can reduce, and that removable discontinuity exists. We removed that factor. Now, in the denominator, we have x plus 3, but be careful. The numerator doesn't go away. We just reduced it to 1. Okay, so we do have a whole, and the whole comes, the x coordinate comes from the factor that we canceled out. So let's set x minus 5 equal to 0, and we can see that the coordinate for this whole is going to be 5 comma something. So remember too that I said twice, right? I said it in class both Monday and then Tuesday or Wednesday, or sorry, both Tuesday or Wednesday or Thursday or Friday, depending on what class you have, that every characteristic has to come from the simplified form if you are able to cancel a common factor. So in order to find that y value, I'm going to take 1 over, I'm going to take the 5 and plug it into the simplified form. So we get 1/8 for our y coordinate. Okay, so we know we have a whole. Just highlight that to kind of grab my attention. For vertical asymptotes, those come from the denominator. Remember, simplified form. So I'm going to take x plus 3 and set it equal to 0 to find that we have a vertical asymptote at x equals -3. Okay, simplified form. Don't forget that. I know I say that a lot. It's important. The horizontal asymptote comes from the degree. Well, the numerator of our simplified form has a degree of 0. There isn't a variable. It's actually x to the 0 power, but anything to the 0 power is 1, so we don't write it. And the denominator has a degree of 1. So since the numerator has a degree that is smaller than the denominator, this is the first scenario in our handy-dandy horizontal asymptote chart. So our horizontal asymptote is at y equals 0. Which means that we don't have an oblique. Sweet. Okay, last but not least are our intercepts. Now for the x-intercept, we set the numerator equal to 0. So 0 is equal to 1. That's not possible. So we don't have an x-intercept. And then for the y-intercept, we simply set y equal to 1 over 0 plus 3. We get 1/3. So our y-intercept is at 0, 1/3. And I'll highlight that too as a reminder. Okay, let's sketch what we know. We know there's a hole at 5, 1/8. So 1, 2, 3, 4, 5. It's going to be kind of there. We know that we have a vertical asymptote at x equals -3. We know that we have a horizontal asymptote at y equals 0. Since we don't have any x-intercepts, right away, I know that I cannot cross this horizontal asymptote. It's on the x-axis. I don't have any x-intercepts. I will not be crossing it. And then I have a y-intercept at 0, 1/3. Okay, let's make our sign chart, see what happens, see what we can determine in order to sketch this. The sign chart is a representation of our x-axis, so the only things that are going to go on this sign chart are vertical asymptotes and x-intercepts. And I totally put an extra line. Here we go. The only thing that we have here is a vertical asymptote at -3. And again, if you want to sketch in what it is, so you have a better visual of what you're dealing with, do it. Okay, we have two different regions. And again, this comes from the simplified form. So region A is to the left of that vertical asymptote. So I'm going to use -4 to check the sign of my y values for every x value in that region. So 1 over -4 plus 3 it's a positive over a negative. So my graph, my function, has negative y values to the left of that vertical asymptote. We can see that it's probably going to be above the x-axis in region B, but just for the practice, let's plug in a value that's greater than -3. So maybe 1. Y is equal to 1 over 1 plus 3. That's a positive sign over a positive sign. We were right. So it's positive to the right of that vertical asymptote. All right, so if in region A we are below the x-axis, the horizontal asymptote helps define our end behavior. We cannot cross that vertical, so we're going to shoot down. On the right-hand side, I'm above. I am going to start at that vertical asymptote. I'm going to come down. I have to go through the y-intercept and include the hole. Now, we don't go through the hole because, and sorry, I don't like the way this looks. We don't go through the hole because that is a value that our function doesn't exist at. Okay, but we kind of jump over it in a sense. Sweet. Okay, let's talk about domain and range. For the domain is all real numbers except x cannot equal -3. And it cannot equal 5. The discontinuities define our domain. So I cannot equal -3. That's the vertical asymptote. And I cannot equal 5 because that was the removable discontinuity. So the domain has to include both of those. If you want to write it in interval notation, we say -infinity to -3 union -3 to 5 union 5 to infinity. And then for the range, we didn't cross over the horizontal asymptote because we didn't have any x-intercepts. So our range is all real numbers except y cannot equal 0. Or we'll say -infinity to 0 union 0 to infinity. Excellent. That's kind of neat because it puts a lot of things together. Working backwards as promised for D. Now this one, we identified the hole. We saw that there was a common factor and the hole was at -2, -4. What was left of our simplified equation is a linear function. So we know that there weren't asymptotes. There was an x-intercept and there was a y-intercept. We found all of that. So I'm going to go ahead and put the hole at -2, -4. 1, 2, 3, 4. And our x-intercept at 2, 0. Y-intercept at 0, -2. Because we have all of these characteristics, we don't need to use our sign chart. We know it's a linear function. So I'm going to connect the hole to the intercepts. And then I am going to make one more point to help me on the left-hand side of my hole to help me draw that line. The slope is 1, so I'm going to work backwards. Okay, so I'm going to do a few points. And then I'm going to connect them that way. Excellent. Now for the domain, it's a linear function, but it does have a removable discontinuity. So we're going to say all real numbers, but x cannot equal -2. Yes, vertical asymptotes don't exist here, but we need to acknowledge the discontinuity like we saw in example E. So we could also say -infinity to -2 union -2 to infinity. Okay, for the range, ooh, I don't know if we did it in the previous one. We might have to go back. It's all real numbers except for the discontinuity, which is at -4. So we're going to say -infinity to -4 union -4 to infinity. All right. I know, that's probably your favorite, huh? Go back with me real quick because I completely, oh gosh, Patterson, forgot to include the removable discontinuity here. For the range, we can't just include it in the domain. So the y value of our hole is 1/8. That is also part of the range restrictions. So rewriting, and my apologies, we go -infinity to 0, union 0 to 1/8, union 1/8 to infinity. Sweet. Okay. Okay, we've done E, we've done D. Let's go back to C. There isn't anything to factor, but I personally like having my polynomials in standard form. So I'm going to rewrite as 5x squared over x plus 3. Okay, there isn't a factor to cancel, so we can say that there are no wholes. There is a vertical asymptote because I do have a factor in the denominator. So x plus 3 equal to 0. It's the only factor in the denominator, so x is going to be at -3. That's our vertical asymptote. The degree of the numerator is 2. And the degree of the denominator is 1. Ladies and gentlemen, there isn't a horizontal asymptote, but there is a vertical. Did I just say vertical? I meant oblique. There is an oblique asymptote. How do we know? The degree of the numerator is greater than the degree of the denominator. Awesome. Okay. We haven't done one of these together before. I'm very excited. Remember, fractions are division. So that's what we're going to do. We're going to take 5x squared and we're going to divide it by x plus 3. Now, since we're dividing by a linear factor, we could most certainly use synthetic division, but I feel like most of us need practice with long division, so that's what I'm going to do. Remember, we do need placeholders. If we're in standard form, we have a quadratic term, but we do not have a linear or a constant, so I put in a 0 there. And here we go. 5x squared, that first term, and I'll actually write it over here so we can see it. Okay, 5x squared divided by the first term in the linear factor. Okay, just the first term. We reduce and we get 5x, so that goes up top, and I'm going to align my terms. So linear term over linear term. Then we multiply through. So 5x times x gives us 5x squared, and we need to multiply by the 3, so we get a positive 15x. What do we do at this point? We change the signs because we're subtracting. So those first terms should cancel. 0 minus 15x gives us a negative 15x. Bring down the next term, start the process all over again. Okay, 2. So we get negative 15x divided by the first term only, and we get a negative 15. So that goes up top. And then I multiply through. So negative 15 times x gives us negative 15x. Negative 15 times 3 gives us a negative 45. What do we do now? We subtract, or we change the signs. The first terms cancel, and we're left with a positive 45. This is our remainder. The remainder symbolizes that x plus 3 is not a factor of 5x squared. Is that what we were testing? No! The remainder doesn't matter to us right now. What matters is the equation that is generated by dividing the numerator by the denominator. What equation comes from that? For us, it's y equals 5x minus 15. Again, doesn't matter that there's a remainder. The remainder tells us that that x plus 3 is not a factor of 5x squared. Not at all what we're trying to check right now. We just needed that equation. Whew, that was kind of fun. Okay, x-intercept. The x-intercept comes from setting that numerator equal to 0. So 0 is equal to 5x squared. We get x squared is equal to 0, so x is 0. We have an x-intercept at 0, 0. And last but not least is that y-intercept, where we set all of y is equal to all of our x's to 0 and solve. Well, in the numerator, we get 0 over 3. Well, 0 divided by anything is 0, so our y-intercept is at 0, 0. Yay! Let's go ahead and sketch in what we have. We have a vertical asymptote at x equals negative 3 and 2, 3. Okay. We have an x and a y-intercept at the origin. Oh, man. Okay, we have an oblique asymptote at y equals 5x minus 15. Holy smokes. Okay, so that means that we have a y-intercept of negative 15. This only goes down to 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, lucky for us, we can find, dun, 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 I'm going to go ahead and find the x-intercept. So I can set 0 for y, and then I can solve. So I could add 15 and then divide. So we have an x-intercept at 3. That's helpful. Okay, I'm going to go ahead and 1, 2, 3. And then I'm going to work forwards and backwards. So our slope is 5. How do we know? Right there. So I'm going to go up 1, 2, 3, 4, 5 over 1. And down 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. Okay. And then I'm going to see if I can get this ruler to line up. There we go. That'll work. Whoo-wee! And then I'm going to sketch that in. Crazy, man. Okay. Ooh, we're going even lower. Thanks for your patience. Hopefully you are using your ruler as well. Okay. Holy guacamole, our sign chart. Now, on example D, we didn't need to use the sign chart because it was a linear function. Here, definitely not a linear function. We need to put our vertical asymptote, which is at -3, on this sign chart, and we need to put the x-intercept. There we go, which is 0. So, this is my vertical, and this is my x-intercept. Okay, do not be afraid of the oblique. The oblique has a very similar function to, I know it's curved, has a very similar function to our horizontal, in the sense that its purpose is to help guide the end behavior. Okay, so we've got 3 sections, A, B, and C. To test A, we need a value that is less than -3. So I'm going to say -4. Okay, so y is equal to 5 times -4 squared all over -4 plus 3. Well, a negative squared is a positive times a positive is a positive. And then a -4 plus 3 gives us a negative. So it's going to be negative in this region. Whoa. Okay, for B, anything between 0 and -3. So let's do -1. Okay, so we get y is equal to 5 times -1 squared all over -1 plus 3. Well, a negative squared is a positive times a positive is a positive. And then we get a positive in the denominator, so this is going to be positive. To the right in region C, to the right of our x-intercept, let's use 1. So y is equal to 5 times 1 squared all over 1 plus 3. That gives us a positive over a positive. So this is also above the x-axis. Here comes the tricky part. Now, in order for us to exist to the left of that vertical asymptote, we are either here or here. Now, if we were up here, right, I would be shooting up and I would have to cross the x-axis. There's 2 problems with that. Number 1, I don't have an x-intercept. Number 2, I would then have positive y values up there, and that's not what my sign chart says. My sign chart says that my y value corresponding to the x values to the left of that vertical asymptote are negative. So we exist here. We exist within this tiny little piece. I could cross this this oblique asymptote. I could cross it over here, but its purpose is to help guide my end behavior. There really is no reason for me to cross it. And I'm going to have to curve and shoot back down, because if I were to curve up, I would cross my x-axis. We know that can't happen. If I curve back down, then I won't cross the vertical asymptote. That makes sense. Crazy, right? I'm telling you, rational functions, you don't know what to expect, but it's exciting. Okay, in the B region, I'm above. Okay, so I'm going to start at the x-intercept because we have to touch that intercept. And I'm going to shoot up by the vertical asymptote. To the C region, that last region to the right, I could cross the oblique asymptote. Okay, its purpose is to guide the end behavior. But I do have to stay above the x-axis, so I'm just going to curve up like that. Oh, crazy, man. I love it. Okay, domain and range. For the domain, we're going to say all real numbers except x cannot equal just -3. It's the only discontinuity that we have here. Or negative infinity to -3 union -3 to infinity. Okay, for the range, this is definitely going to come into analysis of what you sketched. I'm going to start from negative infinity. And I'm going to say, oh golly, okay, so this is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I'm going to say maybe -24. Inclusive, because that's where I hit. Well, maybe I'm a little below, so I'm not going to say inclusive. Let's just be on the safe side, right? Union, I do hit 0, and then I shoot up to infinity. Now, I guessed that this was approximately -24. If you had a similar situation, I would expect you to guess to the best of your ability. You wouldn't want to say, oh, it's -10. That is definitely not accurate. Okay, whew. So once you've completed the notes, we're going to revisit this in class on Monday, and then you will hopefully be ready to attempt the homework.